zeros. And now with Gaussian, so let's say we have 1 0 0 0 0 1 1 0 0 0 1, and let's say here we have 1 2 and 3. So if you can reduce your system to this, then this will be Gauss-Jordan elimination. So basically this is the difference between these two. They are related. So the system, you can solve it until you have dealt with these zeros 1 2 3. Immediately after that, you do what we call back substitution. So this is Gaussian elimination, this is Gauss-Jordan elimination. Okay. Now let's focus on this Cramer's rule. So the system we solved using different methods is this system. I'm just going to copy it. And explain the concept of Cramer's rule. So we can solve it here. I'm going to record now. I didn't see it's recording. Okay, it's fine. So we are given this system x1 plus 2 x2 plus x3 equals to 4. We have 3x1 minus 4x2 minus 2x3 equals to 2. 5x1 plus 3x2 plus 5x3 equals to minus 1. So the first thing that we do, we can write this in an argumented, let me reduce this, in an argumented matrix. So this will be 1, 3, 5, 2 minus 4, 3, 1 minus 2, 5, and we have 4, 2 minus 1. Okay. Now we let A to be equals to our coefficient matrix, which is 1, 2, 1, 3 minus 4 minus 2, 5, 3, 5. So this is our A. Now we determine the determinant of A. So the determinant of A is equals to 1 minus 4, 3 minus 2, 5 minus 2, 3. I think at this point you should know how to determine the determinant. Okay, so this is how you hide. So we have minus 4, 3 and minus 2, okay, plus 1, and you must remember I'm also using signs. So we have positive, negative, positive, negative, positive, negative, positive, negative, positive. So I'm using this row here. So we hide this way. So this is 3 minus 4, 5 and 3. Okay. So let's check. We have minus 20 is 1, minus 20 plus 6 minus 2 into 15 plus 10 plus 1, and then we have 9 plus 9 plus what? 20. So I hope you are also calculating that. If I remember, the correct answer, I think it must be something like 35. So we have minus 14 minus 16 plus 29. So what are you getting? I'm getting a different value. I'm getting minus 45. Could you please check? Let me check what I got that time. Because once it's wrong, everything will be wrong. I see it's minus 35, must be the correct one. So this means I made a mistake somewhere. Okay. Let me check if I copied the system correctly. I think the system is okay. Let's go and check our mistake. Where did I make a mistake? So this is how I hide it. The answer is minus 35, the correct one. Are you getting minus 35? Or it's okay this way? You should just write minus 35. Okay. So the correct one must be minus 35. Okay. Now, immediately after that, you determine the determinant of AX. So what is AX? So I'm going to write it down. So if you check here, we have what we call a constant vector is 4, 2 minus 1. So I'm going to replace the first column by that is 4, 2 minus 1. Then we have 2 minus 4, 3, 1 minus 2, 5. Then you have to determine this determinant. So it's going to be 4 minus 4 minus 2, 5 minus 2, 2 minus 1 minus 2, 5, and then plus 1 is 2 minus 4 minus 1, 3. Okay. So you compute that determinant. Answer here, I don't know. So you're busy computing that to give me the answer. I'm also doing it. What is your answer? Okay, the correct answer will be minus 17. Now you determine AY. Okay, this is in general, but based on what we are doing, basically it's supposed to be, let's just use the variables that we have here. So this is AX2, this is X1 here. So the determinant will be equals to, is it 4, 2, 1? No. My mistake. Let's start. We are replacing the second row by 4, 2, second column, 4, 2 minus 4. So let's go and check the matrix. So we are replacing this guy, the middle one. So we keep the 1, 5, 3, and so here we have 1, 3, and 5. 1 minus 2 and 5, if I have copied correctly. And if you compute this correct, it's going to be minus 105. Then we have A, X. I don't want to go to the next page. I want to finish it here. So this one, you have 1, 3, 5, 2 minus 4, 3. And we have 4, 2 minus 1. You determine the determinant. You get 140. Okay. Now, x1 is equivalent to the determinant of a x1 over the determinant of a, which is equivalent to minus 70 over minus 35, and this is equivalent to 2. And then x2 is equivalent to the determinant of a, x2 over the determinant of a. This is equivalent to minus 105 over minus 35, and this is equivalent to 3. Now, x3 is equivalent to the determinant of a, x3 over the determinant of a, which is equivalent to 140 divided by minus 35, and this is equals to minus 4. So our solution is 2, 3, and minus 4. So this method is called Cramer's rule or determinant. So if I ask you to use the determinant to determine the solution, I'm actually referring to Cramer's rule. So this is the method. Okay. So in the previous class, I said we are also going to discuss solutions. We are still under matrices. We are not yet on the eigenvalue problem. So solving a system of equation using matrices. So here, this is just a discussion. Now we have solved this one using Gaussian elimination. So what we want to discuss is the form of solutions. So there are 3 types of solutions when you solve a system that you can get. The first solution that you can get is called a unique solution. So you get a unique solution when you have a solution for x1 equals to something like, in this case, x1 was 2, x2 is equals to 3, and x3 is equals to minus 4. This is unique. We have a value for x1, for x2, and for x3. The second solution that you can get is infinitely many solutions. Many solutions. And the third one is infinitely many solutions. When you solve a system of equation and you end up with, let's say it's 3 by 3, 0, 0, 0. So let's say you have 2, 1, 3, and here you have 1, 4, 3, let's say 7, 1 here. If you end up with this row of zeros, you'll end up with many solutions. In this case, you can let's say maybe you are solving for xz, and we can let z to be equals to t. And if z is equals to t, then you substitute into that equation. You substitute into that equation to determine the value of x and y. So in this situation, you have infinitely many solutions. And then the last one, you have no solution. So no solution occurs when, let's say for instance, I'll just use this one here. If here, okay, let me just do it in detail again. It's going to confuse you. Let's say you have 1, 4, 3, 7. We have 2, 1, 3. And this one, let's say, is 5. And here we have 0, 0, 0. And this here is 4. From high school, we know that if we have 0, x equals to 4, you can clearly see that these two are not equal. There's no way this can be equal. 0 equals to 4. This is the case. 0 is equals to 4. So in this case, we say that we have no solution. So this means we can have unique solution, infinitely many solution, or no solution. What I'm saying is that you'll be using Gaussian elimination or Gauss-Jordan elimination method. So using these two methods, you might end up with one of these solutions. So I want you to be able to determine those solutions. So here they're explaining, I'm going to maximize it. So here they're explaining that the first one, we have unique solution, infinitely many solution, and no solution. So the first two, if you end up with the first two, you say the system is consistent. So in one of the questions in the assignment, I said test for consistency. So how do you test for consistency? You solve the system. If you end up with this one of these two solutions, then you conclude that your system is consistent. If we end up with no solution, then your solution is your system is inconsistent. So that's what you're going to do there, okay, in that problem. Now, if you are given a system, you have two methods that you can use. You can use Gaussian, we are discussing Gaussian elimination or Gauss-Jordan elimination method. So what I wanted to discuss this way, the raw echelon form and reduced raw echelon form. So you can, in the question papers, you'll end up with this weight, these two weights. So this one is when you use Gaussian elimination. This one is when you use Gauss-Jordan method. Okay, there they're indicating Gaussian elimination, Gauss-Jordan elimination. Okay, so what it means is that if you solve the system and you have a leading entries here, I don't know which one are those one. If it's 0, 0, 0, and the rest here are non-zeros. This, if you reach this point is called raw echelon form, if you end up there. And if you solve the system to reach this point, 1, 0, 0, 0, 0, and this is 1, 0, 0, 0, 0, 1. And we have a solution here, 2, 3, 1. So this means we have reduced your system to raw echelon form. Okay. So here they're just illustrating the process. Okay. They're illustrating the process. So here they're showing that this is in a reduced raw echelon form. But this is, they've given, okay. They are showing, you can clearly see that this one is in a raw echelon form, this one is in a reduced raw echelon form. Basically is what we have discussed there on top. Okay. So that's what I wanted to highlight. Okay. Now, cancel. Let's go back to, I'm going to go back here. I'm going to chart attachment, upload from the computer, desktop. We are no longer writing examination, those are last year exams. What did I want to share? I want to share this one, the one I just discussed. So you can take it from the chart. And the other thing that I wanted to share, what else? Let's go to matrices and check. Oh, now I remember. Your homework. Okay. So I'm going to, let's just check what is that I have just shared. Okay, here, remember I just discussed with you solutions of linear equations. So basically here I said test for consistency and solve. So I've given you 3 equations. You can clearly see this one. You can just do a back substitution to determine the value of x. You will determine the value of x, y, and z. So this is for practice. So you do back substitution, you can clearly see that this system is consistent. You'll be able to, it's unique, it's a unique solution. You'll get the value for x, for y, and z. Now, I've just given you space to solve for that. For this one, you have to solve it. You have to write it in an argumented matrix and solve. So it will be 1, 1, 1, 0, 1 minus 3, 2, 1, 5, and you have 2, 1, and 0. So you have to solve. So the way I've done it, one of them must give you no solution, and the other one must give you infinitely many solutions. And the next one is this one. Also, you have to test for consistency. Okay, now I'm going to move to the next topic, which is the eigenvalue problem. I don't remember where I put it. Oh, it's here. So the eigenvalue and the eigenvectors. Okay. So next year, 80 to 100% of the students in my class will be in Maths 2. Okay. So those who are very serious, they'll manage to pass because this is continuous assessment. You can pass as you go if you focus. And I'm also lenient. So these eigenvalues and eigenvectors will be used next year to solve a system. Okay, we have what we call differential equations. Okay, so next year they will introduce you to differential equations. So these differential equations, they are used to model a real life system. And these differential equations and system of differential equations, system of differential equations. So once we write system, this means we'll use whatever you have learned from matrices and eigenvectors to solve differential equations. So when you solve this differential equation using matrices, this eigenvalue and eigenvectors will be required to solve the system. Okay, you must remember that next year. So this basically will be used there to solve this system which models real life system. For example, those who are doing electrical engineering, we have what you call circuits. Yeah? We have circuits. So these circuits can be solved using circuit equation can be solved using eigenvalues and eigenvectors. Okay, so this I'm just showing the importance of why we have to do these eigenvalues. So they help us to solve real life problems. Okay, so in many applications of matrices to technological problems involves oscillations, vibrations, and equations. So for those who are doing mechanical engineering, oscillations and vibrations will be part of what problems that you will solve now and in future. Okay, so here we have a system. So our system will be in a form of, remember, one of the methods that we used to solve it was matrix inversion. So we have a system like AX equals to B. So that's where we'll start. Okay, so here we have a coefficient matrix A and a vector of variables A, X equals to lambda multiplied by X. So, but basically this system is in that form, okay? Okay, where A is equals to that is a square matrix. So A is a square matrix of coefficients matrix, and lambda is just a number, basically, it's a scalar. Okay, it can be 2, 3, anything. Clearly, when we solve this system, we are not clearly we know that X equals to a 0 vector will be a solution to this system, but we are not interested in that. Yeah? It's not useful to us. It's a solution for any value of lambda, and it's not normally useful. Okay, so we are not interested in that. Clearly, we want a solution where this X, vector X is not equals to 0. That's what we're interested in. The values of lambda are called eigenvalues. So they are called eigenvalues. Okay. And sometimes they call them characteristic values or latent roots of a matrix A. So those are different names given to lambda. And the corresponding solutions of these given equations, this solution, okay, now once we have determined the values of lambda, you solve the system. The first thing that you are going to do, we look for the values of lambda. Immediately after that, we solve the system. This system, when we solve this system, we get a solution. And that solution is called eigenvectors or characteristic vectors of A. So when you solve using this eigenvalue problem, we're actually looking for two things. We're looking for eigenvalues and eigenvectors. Okay. Here they are showing this is exactly what we did when we introduced matrices. This is a linear equations. So this is the equation. Immediately after that, we write it in a matrix form. In a matrix form, this is how it looks like. Okay. If K is equals to a 0 vector, the system is called homogeneous. Okay, this is important for MES2 also, to know what is homogeneity, when a system is homogeneous. And if K is not equals to 0, the system is called non-homogeneous or inhomogeneous. Okay. Now we are going to basic result in algebra. Now consider the system, which I said is this one. We have a which is a matrix of coefficients, and X, which is a vector of variables, and K, which is a vector of constants. Now, we are concerned with the nature of solutions. If any of this, if we have any solution for this system, we shall see that this system only exhibits 3 solutions. The system is consistent and has unique solution. It's just exactly what we have just discussed. The system is consistent and has infinitely number of solutions. A system is inconsistent and has no solutions. So we will end up with only these three solutions in a system, okay? There are two basic cases to consider. So here, I'm actually explaining consistency using a determinant. Remember in the previous one, we said we have to solve the system and get then after solving the system, then you can decide if it's consistent or inconsistent. But also you can borrow from our knowledge of determinant. If the determinant is equals to 0, what does that mean? If the determinant is not equals to 0, what does that mean? Okay, now we have case 1. The determinant not equals to 0. What does that mean? It means that our inverse exists. Remember, we are talking about AX equals to B. This system can be solved using matrix inversion. So using matrix inversion, you have to know that the inverse exists. So in this case, the inverse exists and we have a unique solution. So that's case 1. Case 2, the determinant equals to 0. So if the determinant is equals to 0, you have two cases. We know that the inverse does not exist. But now what happens? What does the value of k play? Now we find out what is this value of k. If this k vector is not equals to 0, the system has no solutions. Okay, if k is equals to 0, then the system has infinitely number of solutions. Okay, so in this case, you can determine this one before even you solve the system. Okay, now here I'm just illustrating, but basically because I've dealt with this problem in detail of solving 2 by 2 matrix. Basically here you can write this matrix as 1 in an argumented form, and we have 2 and 1, and this is 1 and 2. So to solve this system here, basically you have to determine the determinant. The determinant of 1, 2, and 1. This determinant is equals to 1 minus 2 equals to minus 1. Now, an A inverse is equals to 1 over minus 1 multiplied. Now, they said what the diagonal. What do we do to the diagonal? Because it's 1 and 1, nothing will change. So it's 1 and 1. We are supposed to interchange this, okay? And then this one, the non-diagonal, we multiply by negative. So this gives us the inverse of this matrix, which is equals to negative 1, 1, 2, negative 1. So this gives us the inverse. Now having the inverse, it means now we can solve the system. Remember, we have AX bar equals to K or B. Let's make it B. Okay, so I'll just write B in this case. Okay, B. So we multiply both sides by A inverse X bar, this doesn't matter, equals to A inverse. So there's supposed to be A here. So B, so we end up with X bar, because if you multiply a matrix by its inverse, the answer is an identity equals to A inverse B. So basically it means now here we can determine X bar to be equals to minus 1, 2, 1 minus 1 multiplied by 1 and 2. So doing that, this will be minus 1 plus 2, it gives us 1, 2 minus 2, this is 0. So we have solved that system, this is 1. So even for the next one, this is the same method that we are going to solve, okay? We're going to solve this one and that one. And if the determinant is equals to 0, then you have to consider those two conditions that they've given on top. I just wanted to show you that. Now we move to the eigenvalue problem. Now here I'm going to go step by step and give you the method. I'm focusing on the method, okay, which we are going to use here. Let's say they say here, consider this system, okay, where A is n by n matrix. It means that it's a square matrix, okay, and X is n by 1 column vector, and lambda is a scalar or a constant. So we are not interested on this. We know that this is a solution, but we are not interested in this solution. Our main interest will be in occurrence of non-trivial solution for X. Non-trivial, basically it means that is when this is not equals to 0, then it's called non-trivial solution. Okay. Now solution steps to eigenvalue problem. So now what do I do here? I make this to be equals to 0. So I transpose, I take this to the left hand side. So we have, this is the case, okay? Now, we have a problem. We know that A is a matrix, n by n matrix. We cannot subtract a scalar lambda from a matrix A. This problem is solved by multiplying lambda by an identity matrix I. Now I'll just explain what I mean here. This is like this. We have a matrix. Let's say we are solving 3 by 3. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay, minus lambda. And we know that this is just a column matrix. So it can be 1, 2, 3. Now, when I started, I said for you to be able to subtract this matrix, these two, this one and that one, they must be equivalent. This means it must be 3 by 3 matrix, this one here. It must be a 3 by 3 matrix. This means we cannot subtract this one from this one. That's the problem that we have. Now, for you to solve this problem, you are going to multiply this guy here by an identity matrix. And the identity matrix of 3 by 3 matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. By multiplying this guy by an identity, it changes it to be 3 by 3 matrix. So now we will be able to subtract this matrix from this one. Okay, that's how we solve this problem. We multiply by an identity. So by multiplying by identity, we end up with this guy here, A minus lambda I, and then multiplied by a vector column here equals to 0. Now, the determinant, this is called characteristic equation. I think this is incomplete. It must be equated to 0. So from this step here, we move to the next step. The determinant of A minus lambda I equals to 0. This is called characteristic equation. This is the first step that I'm going to always do immediately. If you give me a matrix, I just go directly to this one. This is step 1 that I'm going to do. Okay, and finally we solve this equation to determine the eigenvector. Okay, so this means there are two equations that we are going to solve. We solve this one, number 1, we solve number 2, and then we are done. Then we have solved the eigenvalue problem. The first one is going to give us the values of lambda. Lambda equals to 1, lambda equals to 2, lambda equals to 3. These are just my values. Now, once we have this 1, 2, 3, you substitute into this system and solve. When you solve, now you end up with eigenvectors. Eigenvectors, so we'll end up with k equals to, let's say, 1, 2, 3, and k equals to something again. Let's say, if it's a 3 by 3 matrix, this means you'll end up with 3 of these guys, k1, k2, and so on. So these are called eigenvectors. You see, they are vectors. These ones, they are scalars. Okay. Now let's do examples. So here we are given 2 by 2 matrix. They ask us to determine the eigenvalue and the eigenvectors. Okay. I'll start by solving the first one. A equals to 4, 1, 3, and 2. So let's go to this node. So we are given this matrix. A equals to 4, 1, 3, and 2. Okay, I said the first step is to determine the determinant of A minus lambda I, and we equate this to 0. So that's exactly what we do. The determinant of, now we substitute our A is 4, 1, 3, 2 minus lambda, and the identity for this matrix is 1, 0, 0, 1. Okay, equals to 0. So this we can just write it in a short notation as 4. Now we have 4 minus lambda. Okay, and then here we have 3. 3 minus lambda multiplied by 0 is 0. So 3 minus 0 is 3. Okay, so here we have 2 minus lambda, and here is what? It's not 0, it's 1. And here we have 1 equals to 0. Now this is the normal determinant that we have been determining. So it's 4 minus lambda multiplied by 2 minus lambda minus 3 equals to 0. So this is a quadratic. So let's solve. This is 8. 2 times 4 is 8 minus 4 lambda minus 2 lambda plus lambda squared minus 3 equals to 0. So we group the like terms. Lambda squared minus 6 lambda plus 5 equals to 0. Now we factorize lambda, and here is 3 lambda. We have 5 and 1, so both of them are negative to give us the middle term 6 equals to 0. So we clearly can say that lambda is equals to 1 or lambda is equals to 5. Now we have managed to determine our eigenvalues. This is called eigenvalues. Immediately after that, I don't want to go to the next page. I want to solve it here. Immediately after that, now we have to solve A minus lambda I, isn't it, K equals to 0. Okay, I want to verify this one, this equation. Okay. Okay, seems like it's correct. I still remember my math. Okay, now how do we solve this one? This is not just a scalar, it's a vector. So I'm going to write it again so that you can clearly see it. This is 4, 3, 1, 2. Let me just put it in a square bracket again. Minus, now our lambda, we have to choose 1 here. So I'm going to solve using 1. So this means I can actually write it on top. 4 lambda equals to 1. Okay, so so this means our lambda is 1 and our identity is still 1, 0, 0, 1. Okay, and here we have, now we can write it because this is K1, K2 equals to 0. Now, let's write this one nicely. So 4 minus 1, this will give me 3. And then 2 minus 1, so this is 3, 1 here. 3 minus 0, it remains 3. 2 minus 1, it remains 1. So this is the matrix I have after solving them. So here I have K1, K2. This is equals to a 0. This is not just a 0, it's a 0 vector. 0 vector, so this means if the other way, to avoid confusion, you can write as 0 vector or you can write it as 0, 0. It's allowed, this one. Okay, but when I look at this equation, they're exactly the same. So basically by multiplying, you'll end up with the same equation. So you can just write 3k1 plus k2 is equals to 0. So we get this equation. Now, 3k1 is equals to minus k2. Now, if we let k2 to be equals to 1, you can let anything here, okay? Then, what is the value of k1? K1 will be equals to what? Okay, I don't like this one. I want it to be nice, man. This one is not nice, but it's allowed. You can do that. You can let it be equals to 1. So you're still correct. But I want it to be beautiful. So K1 equals to minus 1 over 3 K2. Okay, so if I let K2 to be equals to, let's say 3, what does that mean? It means that K1, now this one is a vector, is equals to, let's see, if I substitute 3 there, my K1 is minus 1 and my K2 is 3. So this is what we call eigenvectors. Okay, now what remains now is for you to substitute 5 here. 5. If you, I'll say for lambda equals to 5 and solve the same way I've done here. I don't know where I'm going to do it. I'm running out of space. I don't want to go to the next page so that when I explain anything, I should remain in the same page. So for lambda equals to 5, so let's see what you are going to get. If I substitute 5 here, it's going to be 4 minus 5. It gives me minus 1. So my matrix here will be minus 1. Okay. And this one remains going to be 1. 1 minus 0 is 1. Now we have 5. We substitute 5 over here, still minus 5 here. So 3 will remain 3. Is that the case? Let's see. I said 4 minus 5, it gives me minus 1. So it's minus 1 and 1. Now 3 remains. It's going to be 2 minus 5. This is going to be minus 3. Okay. So I have 3 and minus 3. And here I have K1, K2, and this is equals to a 0 vector, which is 0, 0. Okay, you can clearly see that again, this is the same equation. We have K1 minus K1 plus K2 equals to 0, and we have also 3K1 minus 3K2 equals to 0. So you can use one of these equations. You don't have to use both of them because they are the same. If we divide this equation here by 3, we end up with K1 equals to K2. On the first one also, you end up with K1 equals to K2. Okay, so my conclusion is that this our one equation, we end up with K1 equals to K2. So what does this mean? It means that if we let K2 to be equals to 1, so what do we end up with? We end up with this K2 is equals to 1 and 1. So now we have managed to solve this system. We have determined the eigenvalues and the eigenvectors. Any question up to this point? Any question? Okay. So this is how you solve this matrix. Okay. So I'm going to solve those three, but I don't think they'll give me what I want. I'm going to Google something. I don't know. I want, this is, we can, when you solve a quadratic equation, so this is related somehow to quadratic equation. When you solve a quadratic equation, you can have three. What we discuss is the nature of roots, of the nature of solution. So we can have distinct eigenvectors, eigenvalues, or you can have repeated eigenvalues, or you can have complex eigenvalues. So what I'm interested in, I must now look for a situation where we have a repeated and a situation where we have a complex. Okay. So I don't know if this one is going to give me that, these two. The only way to find out is to solve these two. Okay. So I want one that will guarantee me that. Okay. Repeated. Eigenvalues 2 by 2 matrix.
And our goal.
Okay, what I want is just a matrix. So I have that matrix. So we'll solve it on our own. Okay. Now let's also look for complex. Okay. Now let's discuss this one. So let's say we are given A equals to 3 minus 18, 2 minus 9. Okay. We follow the same thing, the determinant. Okay, by this point now I must use shorthand notation directly. Okay, so we are solving the determinant. So it will be 3 minus lambda minus 18 2 minus 9 minus lambda, and this must be equated to 0. So we have 3 minus lambda minus 9 minus lambda plus 36 equals to 0. Now we multiply, we have minus 27 minus 3 lambda plus 9 lambda plus lambda squared plus 36 equals to 0. So this becomes lambda squared plus 6 lambda plus 9, and this is equals to 0. So here we end up with lambda equals to minus 3 twice. You can factorize. Let's just factorize. Okay, lambda, and then this is 3 and 3, and the sign is negative. Let's see. Just wanted to make sure. You see, I made a mistake, so it must be positive. So it's positive 3 twice. Okay. Now let's solve using this method. Now we must solve for this one.
I think it's negative.
It's negative. Okay. Or the middle term must be positive. Okay, yeah, I think it's positive. Thank you. So positive, negative here. Okay. Now we substitute into that equation. We said I want to use shorthand now so that you can, when you write, you save time. That's the reason why I'm using shorthand. When you write exam, this is equals to a 0 vector. Now, the matrix that we are substituting in is this one. 3 minus 3 is going to be 6. And this is minus 18. Now this is 2 here. Now minus 9 plus 3 is going to give me minus 6. Okay. So this is the equation that I'm supposed to solve. So this equation, if you check, the top one is actually the same as the one below. They have multiplied the one below by 3 to get the top one. So these are the same equation. You can take 3 out as a common factor. So we have 2k1 minus 6k2. We'll use this one equals to 0. Now we make k1 the subject. This is equals to 3k2. Okay. Now, if you let's let k2 to be equals to something. Let k2 equals to 1. Remember, I said here a student can use any. Me, I'll just check for consistency. So if you choose k2 to be 1, you must be consistent with your choice. So one student can choose k2 to be 100, to be 3, to be anything. So usually I choose the simplest one, just to simplify my problem. Okay. So what it means that this guy here is equals to, let's see, k2 is 1 and k1 is 3. Okay. Now, to determine, because you have twice, you have 2 minus 3 here, the eigenvalues, we must look for k2. So if it's repeated, the mathematician resolved to use this. So this is 2 minus 6 k1, k2 equals to 3 and 1. So we equate it to the answer that you got there and solve. Okay, so usually to differentiate between the one that I have on top and this one, I make it to look beautiful here by solving for lambda. So when you read my solutions, I usually use lambda mu1, mu2, just to differentiate. Okay. So if you multiply now, you can clearly see here, can still use, where does the 2 next to minus 18 is 6 actually. Okay, thank you. This is supposed to be 6, yeah? According to the, okay. It's still the same equation, okay? So this will be, sorry, 2 mu 1 minus 6 mu 2 equals to what? To 1. What I'm trying to say is that if you divide the top equation by 3, it's going to give you the same equation as the one below. Okay, so we can just use this one. So let's solve. We want to make mu1 the subject. So this is equals to 1 plus 6 mu2. Now, I said you are making mu1 the subject. So it's mu1 is equivalent to 1 over 2 plus 3 mu2. I said my choice is always to try to take to the simplest form, to write mu in the simplest form. So if I let mu2 to be equals to 0, then it implies that mu will be equals to 1 over 2 and 0. So like I said, the choice is yours. It will depend on what you choose. I decided to choose 0. You can choose anything. Okay. So now we have managed to solve. This is how you solve repeated eigenvectors. Okay. So now we are left with the last one, the the complex one. Okay, the complex one will not be complicated here because we are not solving a system. So next year when you solve a system, it will be a little bit different, which I'm not going to discuss here. I'll leave it to Ms. 2 lectures to deal with that. So we are done with this one. The next system that we solve is 0, 1, minus 2, minus 2. You can let this to be A, doesn't matter. So we follow the same steps. We are looking for the determinant. Let's just go directly to the determinant. So the determinant will be lambda minus lambda here. So it's 0 minus lambda. So minus 2, 1 minus 2 minus lambda. And we equate this to 0. So we have minus lambda minus 2 minus lambda plus 2 equals to 0. So we have 2 lambda plus lambda squared plus 2 equals to 0. Simplifies to that. So let's vectorize, or let's rearrange it. Lambda squared plus 2 lambda plus 2. The thing is, you cannot factorize this. If you cannot factorize this, you can use quadratic equation. The lambda equals to minus 2 plus or minus the square root of 2 squared minus 4, and my a is what? Is 1, my c is 2, all over 2 multiplied by 1. And this simplifies to minus 2 plus or minus the square root of 4 minus 8 all over 2. And this gives me minus 2. No, this is wrong here. This gives me minus 1 plus or minus 2 I. Okay. Let's see if this is the case. Minus 2 plus or minus the square root of minus 4 over 2 equals to minus 2 plus or minus root 4 multiplied by root minus 1 all over 2. But from the knowledge of complex numbers, we know that I is equals to root minus 1. So this is minus 2 plus or minus root 4 is 2. So this is 2I all over 2. And this is equals to minus 1 plus or minus. You see, I also made a mistake. But it makes me interesting by just jumping to the answer. I just like doing that. Makes my mind to work. Okay, so we no longer need this part. I was just explaining. Because remember, this is recorded. You'll be able to see that. We no longer need this part here. We have managed to get the correct one. So now let's substitute. This means here it means that we have lambda 1 equals to minus 1 plus I, and lambda 2 equals to minus 1 plus I. Now we have to substitute here. So we have to solve minus 1. Is it minus 1 there? Just to confirm, minus 1 plus minus I or plus I. We can take any one. 1 minus 2 minus 2 minus 1 minus lambda. And we are looking for K1, K2 equals to 0. So let's try to simplify and see. So we have 1 multiplied by 1 plus I minus 2. This is 1. Let's try to simplify this one. It's minus 2. Let's try to simplify it completely before we go to the next step. So it's going to be minus 2 plus 1. It's going to be minus 1. Minus 2 multiplied by minus I. This is going to be plus 2I, if I'm not mistaken. So this is K1, K2 equals to 0. So even in this case, these two guys, equation 1 and equation 2, they are actually equal. You have to multiply the above equation by something to get equation 2. Okay? I don't know. Maybe you can help me. I know they are equal. The difference is a multiplication. They have multiplied it by something to get something there. Okay? Can you check for me?
Sir, I think the minus 2 is being multiplied with the I. So it should just be minus 1 plus I.
Minus 1 plus I.
Yes.
Everyone has checked that, ne? Plus I.
Yes.
So you'll verify that if that is the case, eh? Okay, what I have just explained now is that these two equations, they must be equal. The only thing that you have to do, I think I've done that for one of the problems last year. Even this one, you just need time. Eh? You have to think. You might find that they multiplied by something, a conjugate or something to get the one above, but I'll show you later. So once you reach this point here, the equation 1 looks simpler than equation number 2. So you just use equation 1 to solve the problem. So it's 1 plus I, K1 plus 1, K2 equals to 0. So from here, you must determine, make one of them the subject of the formula. I usually make K1, I don't know what. So K1 is equals to minus K2 over 1 plus I. Okay, so from here, you can clearly see that we let K2 to be equals to 1 plus I. K2 is. So if K2 is equals to 1 plus I, so this means K1 will be equals to minus 1 plus I. So I just wanted to show you. So now this will be your eigenvector. Okay. So with the complex numbers, once you have determined K1, you can use K1 to determine K2 because they just differ in signs. I hope you understand that. So to determine K2, because these are conjugates, you can clearly start with use 1 minus I. So how are they going to differ? Or we can just compute it again. You substitute minus, here is going to be what? Plus I and solve. And then determine the value of K2. Okay? So I think the best option is to do it and then compare the answer. Then in future, you'll know what value you are going to multiply with. It has been long since I do this. Okay. Okay, I want to see where I can do that. So it's going to be minus, let's do it, minus, so using, what are we using? I think one of them is wrong here. Supposed to be minus. Who's making noise? Okay, now we are going to substitute minus 1 plus I. Okay, minus 2 minus 1 minus I. And what are the other terms that we have? They're minus 2 and minus 1. Minus 2 and 1. And then we have K1, K2 equals to a 0 vector. Okay. So again, you can just use equation 1. So this will be 1 minus I, is that the case? Plus, this will be K1 plus K2 equals to 0. So you make K1 the subject. K1 is equals to minus K2 divided by 1 minus I. So if you let K2 to be equals to 1 minus I, so it means that our second vector, eigenvector here will be minus 1 and 1 minus I. So now let's see how they differ. Let's see how they differ. So if I take out, let's see, if I multiply the top one by minus 1, let's see what I get. I don't see the difference. Yeah? Will you help me see the difference between K2 and K1? And check if I've done it correctly. I didn't make any mistake there. You must check my substitution.
So from what I see, the only difference is that the 1 plus I on K2 is the conjugate of the first one.
Is the conjugate of the first one.
Yes.
Yeah, and also check if I didn't make a mistake. Yeah? So only what changes the conjugate. Okay. But for safety, I think just compute it. Compute K1 and K2 to make sure that you get the correct answer. Compute K1 and K2. Okay, I think I'll stop here. I'm not done with solving the eigenvalue problem. So in the next class, we are going to discuss eigenvalue of 3 by 3 matrix. And after that, we do what we call diagonalization. So if you check the notes here, we are here. So we still have to calculate the eigenvalue and eigenvector of 3 by 3 matrix. And immediately after that, we do what we call diagonalization of a matrix. So when you diagonalize this, we are going to look for eigenvalues, eigenvectors, and then we determine the matrix P using eigenvalues, eigenvectors. Okay. And immediately once we have, so this means if this will be for what we have just calculated, this will be K1, K2, what we have calculated will give us P. Immediately after that, we determine P inverse. So this means we are looking for an inverse of this matrix. Then we determine it here. We determine P inverse, and then we prove that D, the diagonal, D is equals to, will be equals to this. The eigenvectors that you got, and here will be 0 and 0. In the first matrix that we calculated, actually here, I want to go to the previous one. There's somewhere where we determine the eigenvectors to be 1 and 5. Yeah, I remember. So it means that this will be 1 and 5. So D will be equals to 1, 5, and this will be 0 and 0. And then we'll have an identity matrix here. This will be K1 and K2. So that process is called diagonalization of a matrix. So that's the process we'll follow. Determine eigenvalue, eigenvectors. You write your P, you determine P inverse. Then we show that D is equals to this. So, and we'll, once what we do for 2 by 2, we extend to 3 by 3, and then we diagonalize that. Okay. So this means this will take the whole period actually. In the next period, we'll only be dealing in the next class with eigenvalues and eigenvectors. Have to complete that. So this will be the end of the class. So I'm going to stop this one. Any questions? Okay, I can see people are leaving. So in the next class, we'll discuss that, the eigenvalue and the eigenvectors. Okay, if